Welcome to the mothership. This is Mr. Sundelka. I'll be your captain on this voyage. We'll look at 3.4, velocity, other rates of change. Calculus in the PM. In case you just joined us, this is calculus in the PM. 3.4. Okay, anyways. So instantaneous rate of change. There's a difference if I just say rate of change. The instantaneous rate of change of a function with respect to x at a, and now a, this is in italics, but this font doesn't show it well. At a, that's a number, like 5 seconds, is the derivative. So, derivative, we can notate it f prime. And we know this definition, provided that limit exists. Okay, fair enough. And we know all the shortcuts, not all, a lot of shortcuts so that we don't have to do that every time, right? And we also know that the derivative basically gives us a formula for the slope of the tangent line at point, right? Okay, now, I said we're going to use lots of speeds and distances and stuff like that that relate to physics, but it's also rates that, I'm just shutting the door. I'm getting distracted. Rates don't have to be just speeds. We could talk about the rate that you make money, dollars per hour, if you're selling hot dogs at a fair or something like this. We could talk about rates that don't even involve time, kind of. And here's one that doesn't involve time. Can you imagine? Find the rate of change, the area of a circle, with respect to its radius. So if you can imagine, I threw a rock into a pond. Boom. It hits right there, right? Half a second later, it's got this ripple that's working out. I'm going to just follow one ripple. That same ripple then gets bigger and bigger, right? And it moves out. Now that's what we're talking about here. Find the rate of change of the area with respect to the radius. So, do you guys get the idea here? That's not even involving time. You could involve time. That's a different, slightly different problem. So, if we want to find the rate of change of an area, we need to have an area formula that relates area to its radius. Do you guys know for a circle? I hope you do. An area formula that pi r squared, right. So, here's something just a little different than you've done before, though. Not much. I'm going to say area as a function of radius. You know how you say f of x? That means x is the variable that you could manipulate and see how it responds. Well, this means area. How does it change? Okay, so that's not too confusing. I'm just saying a with as the radius changes. Because I could give this in terms of diameter, couldn't I? And I'd call that a of d, but we won't give it. Okay. Now find the rate of change of the area with respect to its radius. As long as I have a formula that has radius in it, according to this, what do I do? The instantaneous rate of change with respect to x. Well, we got the letter r, radius, is the derivative though. So if I know this is the area formula, how do I find the instantaneous rate of change at any given radius? Like as this radius gets bigger. A prime, right? The derivative. I won't actually use the definition of the limit because we know some shortcuts. A, keep to this. The derivative with respect to the variable r is, well, pi is a number, right? It's not a variable. 3.14159, blah, blah, blah. So, hey, 2 pi r. Have you ever heard of this before? Circumference. Okay. You'll notice that a lot of geometry formulas are related by calculus. Now, I didn't ask for the units here, but let's just think about the units. Obviously, my next problem would be in centimeters. So if I did a radius in centimeters, I'd get centimeters squared as my units, right? Does that make sense? Okay. I'm just putting it in blue because it's not really part of the formula. I'm just thinking through the units. Now, what's the other notation for a derivative? A prime, or I could have written dA by dr. Does that make sense?
Yeah.
Okay, that's the other way. If I just think of it as A equals pi r squared. Now, it's the same information, so I'm just going to say dA by dr. Now, the reason why I'm doing this is it's easier to picture the units if you think of this notation. And that d really means, it's a differential kind of thing. It's the I won't tell you, actually. I'm going to get you to tell me. This is the limit of, what formula is this? Slope formula. The change in y over the change in x is really what it is, right? So I didn't need to box it off. Change in y over change in x. This really means the change in area over the change in radius. It's the slope formula applied to that with that limiting thing. Now, unit-wise, just from dA by dr, what would you say the units are? Well, what's the change in area? What's the area measured in? Squared. Centimeters squared per centimeter. Now, it comes out to be centimeters. But really and truly, you should think of this, if you're talking in this problem here, that for the area changes by, if I got a number of like 20, that means 20 centimeters squared it grows by for every 1 centimeter of radius increase at that point in time, or point in the circle, not time. Now, I say include units for B here. So it does actually come out to be just centimeters when they cancel. Evaluate the rate of change of the area at 5 centimeters and at 10 centimeters. And we'll include units. What do I do for this problem? Just put it into our, we just put it into our formula. So, I'll even pause the video here. Okay, so we're using centimeters squared per centimeter because, yes, it does cancel down to centimeters, but this is more descriptive and it tells you what the rate's all about, right? Philosophically, it's not truly the circumference that you're talking about. You're talking about a rate of change. Circumference is a length, but it comes out to be the same number. So it's sort of like impulse and momentum change. You guys study that yet? Okay, I won't get into physics. Motion along a line. If an object's moving along the axis, typically we'll say the x-axis, we may know its position S on that line. All right. In physics, I use X all the time. In math, we use S. So I don't know why they use S of t, but they do for position. And I just say, oh yeah, right. In physics, you rarely use S. You use either d for distance or x for a distance horizontally or something like that. Just to relate things. And I'll keep relating things to physics because a lot of you are familiar with this. Now, instantaneous velocity. That's the derivative of the position function with respect to time. At any time, the velocity is given by, so the velocity, it's just the derivative of whatever position function you have. Okay? Who cares about, it is the limit, but you'll never really use that. You'll use your shortcuts, right? So that's what this is. You got to remember though, velocity is really the derivative, the first derivative of the position function. Okay. Speed. How is speed different than velocity? Physics people will know this, but speed is the absolute value of velocity. Positive or negative direction is not important. So just do the derivative and take the absolute value. If you're not in physics, I will review this right now. If I say, typically, if I just draw to the right is positive, to the left is negative, right? And I say I'm traveling to the right at 40 kilometers per hour, we call that 40, positive 40. The way I'm standing with my arm this way, that's going west, right? If I'm going east, the way I've drawn my negative sign there, we would just say negative 40 kilometers per hour. Does that make sense? However, in your car, You just say 40 whether you're going west or east, right? Or north or south. Speed is without direction given or any positive or negative. But typically, well, if you were talking about velocity, you'll give a positive or negative. Physics people know what I'm talking about, right? Yes. Don't fall asleep on me. Okay. Definition. Acceleration then. Acceleration is the derivative of velocity. It describes how quickly, I guess you could say, something's speeding up in a sense. If a body's velocity at time t is given by the v function, then the acceleration is that derivative of the velocity function. Or you can think of it as the second derivative of the position function, okay? Now, that's what acceleration is. And it describes the change in velocity over an amount of time, in a sense, okay? Intuitively, a lot of people know what acceleration is about, even if you haven't taken physics. If you really hammer down your foot on a small car that's kind of like souped up a bit, something like Zach drives, you got a lot of acceleration. You speed up quite quickly, right? If you're driving a big truck, heavy, weighed down, and you've got one of those gears that you know this, if you're behind a semi on Victoria Avenue, if you could choose which lineup you're going to be in, there's a semi here, it's not going to accelerate fast, so you go to the other line, even though there's 3 cars there, right? Because chances are you'll get going faster. Everybody can accelerate quick. Intuitively, we understand this. That's acceleration. You're intuitively understanding. Now, you won't have to memorize this. It'll be given in problems, but just to relate it. In some problems, you might be told that an object is falling with an acceleration of 32 feet per second squared. The book doesn't use s squared, but we'll use s squared. S is fine for seconds as an abbreviation. Just don't make your s's look like 5s. Okay. So, feet per second squared, 32. You'd be given that if you're talking about feet. If you're in this textbook, though, actually sometimes they might not give it right in the problem. But on an AP test or my exams and stuff, I will give whichever you need. If you're talking meters per second squared, 9.8 is good enough. And negative, if you want to take direction into account, it's falling, yes. Yes. 9.80 if you want more significant digits, but we're not worried about it here.
Is distance s?
Yes. I don't know why. Well, actually, I do know why. In math, they don't use d for distance and position and stuff because it would look stupid if we went dd by dt, right? That's why I think that dx by dt makes sense. But the books, and this is not just this textbook, it's on the AP exam, you'll see s as a position function often. I don't know why they chose s, but they did. Math books tend to use s's. Reading the distance graph. Okay. This is where, I know you guys know how to manipulate equations, and you did it in grade 10 with speeds and distances, stuff like that. This is the trickier part, looking at the graph and what does this describe. First of all, we won't even worry about acceleration right off the bat, but this is the distance axis, the y-axis, time, x-axis. Now, if I was to walk this out, and I know this won't get recorded for Savannah on the video, I'm going to call this position 0, right? Right where I'm standing. What does this mean I do? Let's say that this is 5 seconds here and then maybe 10 seconds there. For the first 5 seconds, what do? So I'm going to walk in the positive direction to my right, your right, okay. And do I start out fast or slow? Slow, speedier, then it seems like constant speed right here. Then I start slowing down. What's right here? 0 speed. Do you guys kind of understand that? So I start out slow, then I start picking it up, and then come to a stop. What happens after that peak there? Velocity 0, it says there. Yes?
You return to your original, well, you're heading to your original.
Exactly. And sort of slow at the start, speed up, slow down to 0. Oh, do I go to, you said to the original spot.
Almost where it's just like you-
Oh, so I'm gonna do this again. I come back to maybe a meter from where I started or whatever. I'm not measuring this. But yeah, this corresponds to a distance somewhere, not quite back to the starting point, but you return in that direction. Okay. Is that making some sense? Okay. So then let's look at the words. So what does this represent? We kind of understand that. Positive acceleration. You're speeding up, this is what you would say in regular speed. The acceleration is 0 because this is flat here, right? The speed isn't changing, and if you took the slope there, it'd be the same slope here as it is right here, is what we're saying, right? Then you're slowing down until you stop. You turn around. Then constant speed for that portion. And come on in, Savannah. Anyways, and then eventually you stop, okay? So we're on 3.4, Savannah. So do we have a general understanding of this? I know you even examined graphs in grade 10. Usually they were linear chunks, but you talked with this. Okay. It's really important there that we do take a look at this. I'm going to just pause this for a second. There's more chunks to this graph here. Let's read here. Particle moves along an axis. We'll think of it as left to right, right to left, whatever. And its velocity is shown in the graph below. Describe the motion. State when the speed's at a maximum. We'll think of meters per second, okay? So the velocity we'll think of as in meters per second. This is not a distance graph. What's my starting velocity here? 0. Okay. Then, what's happening between here and here? I'm accelerating. I'm changing speed. Would I be accelerating if this was a straight line? Still, it's changing speed, right? Would I be accelerating if it was a curved line this way? Yeah. How is that different than this curve? So here, I'm getting faster and faster. I'm picking up speed. It's sort of like, you know, when you start off running, well, no, maybe it wouldn't be quite like that, because I'm picking up speed kind of slowly at the start, and then all of a sudden I'm picking up speed tremendously for the next, maybe that's up to 4 seconds or something. Okay. So I guess we should jot something down. It accelerates and it's positive. We're going to use the word positive acceleration to be picking up speed. So, positive acceleration. From about 4 to 8 seconds. This plateau here. Am I moving at all? Yes. Because I still have a speed. This is not a distance time graph. Okay, good. Okay, I heard the word constant. What is it?
Constant speed.
Constant speed. It's not changing. You guys in physics and thinking about this a lot lately? Okay, so it's... Okay. So this is kind of old hat for you guys. So this is constant velocity. I'm going to maybe quiz the people who aren't in this more, or who aren't in physics. So I'm going to put down acceleration is 0 at this point. When I say positive acceleration, acceleration is greater than 0 at that point, right? Okay. Now, my speed from here to here changes from, say, it's 7 or 8 down to 0 again. So, negative acceleration, okay, I'm slowing down in this case. Negative acceleration, but still going in which direction? To the right or to the left? I'm still going to the right. I'm still above the time axis, right? So that is like braking, right? Okay, so slowing down. And am I slowing down quicker at the start or at the end? At the start, I'm really braking hard, and then I kind of ease to looks like you stop right here. You can't get across this V line, this axis, without stopping, right? Okay. So here, we're going to call this negative acceleration. But I could say instead of negative acceleration, I'm getting used to this idea. A is less than 0. Negative, right? Acceleration. But I'm going to put down with positive velocity. Now, a lot of greater than, less than signs, but the velocity is in the positive direction, to the right. We're going to talk about right, left. Does that make sense? Okay. So you can have negative acceleration and be moving to the right. Now, is it possible to have negative acceleration and pick up speed?
Yeah.
Yes. What does this mean when I am below the time axis? This just means that my speed, okay, I've braked. And then now I'm going to go to the opposite, the left direction. This is all in the left direction up to this point here, right? From here to here, you're traveling left. Now, I'll pick up a pen again. So, for a brief second, stop. So V equals 0, right, at that point. Okay. And for this portion here, is the acceleration positive or negative? Okay.
Actually, no.
Yeah.
With a sign, S-I-G-N sign. It is still in the negative direction. It's still pushing you in the negative direction. It's abstract. Negative acceleration, but it's speeding up in the negative direction too. So this is, I'll write it out because it seems confusing. Negative acceleration. So in other words, acceleration is less than 0. And negative velocity, that just means it's going the opposite direction though. It doesn't mean it's at a standstill. Now, when I say negative velocity, I just mean I'm going to boost this up so I can see it better. V is less than 0. All that means is I'm traveling the opposite direction. Now, from here to here, it's kind of speeding up. Now, we're using the word speed and velocity interchangeably, too, because this isn't this speeding up? If I'm saying speed, it is speeding up. It's picking up negative velocity in the negative direction. Yeah, it's confusing. It's like picking hairs, but the way, just because you said speed, I want to make sure. Speed kills, right? It does, actually. How about it's picking up in the acceleration is positive again. Now I'm going to use this again. So positive acceleration. What about the velocity? But the velocity is still negative. It's still underneath the axis. That just means I'm going to the left, but braking. You said you were picking up speed. Did you say picking up speed? No. Okay. So this is really because the acceleration's in a different direction. I thought you did, actually. This is just braking in common terms, right? How can you tell then when you're braking? You can't tell you're braking because the acceleration is positive or negative. What has two conditions for braking? Yes.
Where your signs need to be opposite.
Exactly. Your velocity could be positive and your acceleration negative. That's braking, or vice versa. Make sense? Okay. And then lastly, there's a stretch here where you sit, stand still, right? V equals 0 for that whole portion. And then you pick up your speed at the very tail. Okay? Now what else? Oh, when's the speed at a maximum? This is the speed graph, but it says speed. Speed here is like sort of, if I'm just making up a number, but the scale 1, 2, or if it's 5, 10, you know, whatever. This is definitely a greater speed actually here, right? Speed. Don't worry about the direction. It just means I was going to the left at a greater rate. And in your car, you never talk about velocity, you just talk about speed. So this here is the maximum speed. And that's confusing. The people, I could tell who's in physics, but who was answering quickest. In the sense, we'll get time to worry about these concepts a little more though, okay? So don't worry. If you're like, physics, yes.
So for acceleration, when it's positive and negative, all that's determining that is whether or not you are accelerating or decelerating, or is it based on whether it's a positive value, like to the right or going to the left?
Okay, I'm just digesting the whole question, and we'll tend not to say decelerating, but decelerating is sort of a common term because we're going to say negative acceleration.
Yeah.
Okay. If I am going to the right and I start braking, that's negative acceleration with motion to the right, so that's braking, right? So that's where you'd often say deceleration, right?
Okay.
Now, if I'm going to the left, I'd say negative velocity and negative acceleration if I was picking up speed as I did this.
So even though you're getting faster, like you're accelerating, it's still negative?
It's negative acceleration strictly because you're picking up velocity in the negative direction. That's why that's why we use the term loosely braking. Braking happens, whether you're going left or right, when the velocity and the acceleration have opposite signs.
And so how would that happen if velocity is going to the left?
Let's talk about throwing an object up in the air. Because there's always acceleration downwards. This doesn't change, right? And it's a value negative 9.8. So when I drop something, it's accelerating downward. When I throw it up, do you agree that this is positive velocity out of my hand,
Yeah.
and it braked when it's at the top, right?
Also negative acceleration.
Negative acceleration with a positively moving object when it goes up. However, it's still negative acceleration when I drop the keys, and it's picking up negative velocity. I drop the keys because I'm breaking in a new pair of hands. It just happened surgically. Anyways, done. Yes?
Yeah.
Okay. Now, oh, it is confusing at times. Oh, yeah, it's confusing. Wow, wow.
Is in order to do kinematic equations again?
Yeah, not quite. I'm just taking a look here. Yeah. Should we move it through these two examples and then give you some work time tomorrow as a whole work class? Is that better? We'll plow through this. Okay. Because I could chop this up into two parts, half and half. Okay, either way, it's two classes. Okay. Vertical motion, up and down. A dynamite blast propels a heavy rock straight up. Launch speed, 160 feet per second. It's about 109 miles per hour. Probably makes no sense to some of you who've never talked about miles. It reaches a height given by this function. Feet and miles are the American system. It doesn't matter, it's just numbers. It's just different units. And you get used to the exam, whether it's at centimeters or inches or whatever. It doesn't make a difference.
There's like no conversions, right?
No, you will not have to know
Oh, okay.
12 inches to a foot, 3 feet to a... 1900. Anyways, how high does the rock go? We're Canadian. Well, what we need to understand, and this is where the physics people have a head start, they've thought about this. But you've seen an object thrown up enough. How high does the rock go? Well, what do we know about the speed, or velocity is a better word, at the top, at the max height? That's where it stopped and then it starts coming down, right? So, what I'm thinking when I hear this is, the only way you can go up and then down is the velocity is 0 at the maximum height. That's really what I'm trying to find, right? Like the height when the velocity hits 0. Okay. Now, where do we go from here? Because this is not like a physics question where we have everything worked. Actually, we kind of do, but anyways, we don't have everything worked out. Well, we need to know the time that it elapses and so on here, because what good is it knowing that the velocity is 0 if I only have an equation for position? How do we go from a position function to a velocity function? Derivative. Okay. ds by dt, or we're going to call it s prime. Okay, so I'm going to go like this. b prime of t equals, oh, sorry, v prime, s prime of t. v of, now my pen's reset. v of t equals the derivative, s prime of. We have the s function up there. So v, as a function of time, is 160 minus 32t. By the way, oh, sorry, I kind of skipped here. S prime of t, I did the derivative, 160 from that, minus 2 times 16, 32t. That's where that came from. I don't know this formula ahead of time. Okay? Now, next thing is, how high does the rock go? I don't know exactly, and I won't know from this equation, but what can I find from this when I know the velocity is 0? I could find the time, though. I could find the time that it takes to go all the way up. That's what we're going to find. So, I sub in, I know it's 0, it's at its max height. Time is equal to 160 divided by 32. Oh. Can you do it? 5. Okay, I skipped a step there. Think of it this way, I added 32t onto that side, divided, yeah, okay. So I kind of skipped a step solving the linear equation. Now, all this tells me is that it took 5 seconds to go up. How do I solve this problem? How high does the rock go? Yeah. Yeah, sub it into your S of, thanks Corey, somebody. Yeah, just the same. Thanks for your patience and understanding with the other person. Okay, 160 times the 5 seconds that it takes to go up to the top, 16 times 5 squared, that's the 5 seconds it takes to go up. That's arithmetic. And basically, it's 400 feet. I don't worry right now if you guys, I'm assuming. 400 feet in the air. That's pretty high. That's a heck of a blast, about 160 feet per second. It's pretty fast, so that makes sense. That's the max height. That's what you were looking for. My goodness. Now, question B. Do I need to pause or questions? No? What is the velocity and speed of the rock when it's 256 feet above the ground on the way up and on the way down? How do we go about doing this then? We know it's going 400, but like 256 here and here, right? How? We could find time. Okay. So we'd use this position equation to find the time, is what you're saying. Okay, because we know the position here and here. Find the times, plural, that it's at that position. It's twice on the way up, on the way down. Then we could find the velocity using those times. Okay, so 160t minus 16t squared is the formula. 256 is the position. 256, 60t minus, what was it, 32t? Or 16 t squared. How do I solve one of these? Oh, it's a quadratic, yeah. Yeah. So I'm going to call it 16. I'm going to move everything to the left. 16t squared minus 160 t plus 256 equals 0. Do I need the quadratic equation for this? You could use it, but say you didn't have your calculator, because maybe this is on a no calculator section. I can actually tell you that most likely numbers this big, this is very doable, but it probably wouldn't appear with numbers this large on the AP exam. But take out a common factor of 16. T squared minus 10t, 256. You guys recognize that one? 16 squared, so it's 16. You could factor this. You are fast. So negative. I'm leaving it out because, okay, 8 and 2. Yep, that works. Okay, so then we set it equal to 0 for each one of the factors. 16 can't equal 0, but t minus 8 can, so t could be 8 seconds, or the time at 2 seconds. That means on the way up at 2 seconds, it's at that spot. On the way down at 8 seconds, it's at that spot. To solve this problem, though, what's the velocity and speed? Oh, well, the velocity, we have the function one just right here, right? So v of 2, 160 minus 32 times 2. Hey, I could do that in my head because that's 64. I think I can. 160 minus 64 is 96. What's the unit? Since I have a number, it's velocity and it was in feet per second. Okay. And it said the speed. Well, in this case, the speed's the exact same, right? What about v of 8? Somebody in physics know, without doing any calculation, what the speed is? It's going to be the exact same, but if you mind blown if you're not in physics because you haven't thought about this probably. So you'd put this in here. Trust us. When you work this out, it comes out to be negative 96. Negative because it's on its way down. Yeah, but we're speed and velocity. And then, like you said, the speed is 96. No regard for direction. Okay. Now, is there a symbol for speed? Just put it in that. If you want to have a symbol instead of write down the word speed, just do this, absolute value. That means speed, but that's going to disappear in a second. My goodness. This is, you guys are like, yeah, we still got C and D to go.
So the speed is 8t, t equals 2 and
Okay, sorry. Oh, it's at 2 seconds and 8 seconds, it's 96 both
8.
times. Yeah. But, like I said, people in physics have thought about this on the way up and on the way down. It's a mirror image of each of the values for velocity, speed. You probably didn't know that. And then don't trust that always, because you'll be given some monkey wrench problem that isn't under the influence of gravity, and then what? What is the acceleration of the rock at any time during its flight? That means come up with a function of time. What do we know about acceleration and velocity's relationship? Acceleration is the derivative of the velocity function. Or you could say the second derivative of this position, but we have VT. VT, I have it underlined in blue at the top of the page, 160 minus 32t. So what's that derivative? This is minus 32, yeah. The acceleration, and this makes sense from what you know. Now I'm going to put units on there after, but just like in metric system, it's always the acceleration is negative 9.8. In the imperial system, it's always negative 32 feet per second squared. Why that? Feet per second squared? I'll put this down first. And this is for the benefit of the people not taking calculus and physics too. Like people who are in, just think of this. Unit-wise, like I said, the d by dt notation is better to figure out units. If acceleration is equal to, we said the second derivative of the position function, right? I could write this as d2 with the s function in it, s of t, if I want. That looks like a mess, but anyways. Now just think. What's the unit of s? Feet, right? You notice that the square is not on the s? Okay. But this, dt, the change in time squared, time is seconds squared. Do you see how you can come up with units? The d by dt or d by dx notation describes units better. It's, if you're ever stumped what the units are, think in d by dt or d by dx notation, and you'll usually figure it out a lot easier. The s prime and v prime doesn't really, if you don't know it ahead of time, you might be stumped there. When does the rock hit the ground? When the position is 0, and we're going to assume it's not the starting one, at time 0 it is, but it'll be the other value. So when the position function is 0. So it's gone up and it's gone back down. Obviously we're looking for that second time, right? So that's when, well, 160, what is it? I'll read on the paper, 160t minus 16t squared. Solve this for 0. I just need to factor this. Take out 16, it's 10t. I know you know. 10 minus t. We've got two solutions. Either 16t equals 0 and t is 0, or 10 minus t equals 0, and that's when t equals positive 10 seconds. It's obvious that it hits the ground the second time around. It starts at 0, hits the ground at 10 seconds. Now I'm going to stop because this is too much. We're going to have to finish up tomorrow. Miss Klimchuk, I said you deserved an award. You've been so quiet today, though, I don't know if you do. Yesterday, she was asking good questions, and she complimented me almost, right? You remember? So I made you an award, and I'll get it up here. It's got gold status. This document certifies that Sarah Klimchuk has achieved gold status. She's a delight to have in the classroom, always polite, asks good questions, except for today. And is usually
It's usually not.
task and time, too. Anyways.